Thank you for joining us. This is Can You Roll Your Own SIEM? I'm Ethan Christ, and I lead the Security Identity Monitoring and Response team at 2 Sigma Investments.
I'm Bret Rubin, and I'm a security engineer at 2 Sigma, focusing on our security event collection and reliability for security-run products.
For those who haven't heard of us, 2 Sigma is a financial sciences company headquartered in New York with over 1,600 employees. And a quick recruiting shout out. We're hiring, so if you're interested, even after hearing our talk, check out careers.2sigma.com. And now on to the main event. Given the maturity of the SIEM product space, deciding to roll your own may not strike you as the wisest of ideas. Let's dig into why we ended up deciding to do it anyway, and why it was the right choice for 2 Sigma. But first, let's see how quickly I can transition past the disclaimer slide. We'll start by discussing the high-level considerations that led us down this path to begin with, and then what made this the right choice for us. Bret will lead us through the technical details of our implementation and give a demo of the solution. Then we'll end on the actual results of this effort and the broader strategic implications creating our own SIEM has had for us. As we first started to think about what our ideal replacement SIEM would look like, we went through a requirements gathering phase. The first thing we looked into was how much data we needed to ingest per day. The existing license of our on-prem third-party platform only allowed us to ingest 1 terabyte per day, and this was a hard cap. Routine overages of this daily rate would lead to loss of the ability to search our data, which meant we had to be constantly mindful and diligent of our daily ingestion amount. This was not a situation we wanted to be in for the next product, given how much staff time it took to track down and remediate heavy loggers. Ideally, we would want a system that wouldn't cap or restrict us, but instead give us the flexibility to collect more without paying exponentially more, or by having confiscatory controls around search. Our platform's limitations led us to not ingest certain large data feeds, such as firewall logs, that can provide valuable signal to our security analysts. Our next consideration was speed of ingestion. Several of our queries feed downstream actions that have some time sensitivity. One such example was identifying interactive root logins to production security systems that didn't occur via our specifically designed single-purpose management system. We were targeting detection for these events within 60 seconds of one happening, which means the logs would need to go from the host in question to being searchable and firing an alert in that time. Reliability was another key requirement. We rely heavily on our logs for forensic capabilities during investigations, so ensuring their accuracy and completeness was critical. We wanted to avoid lossy protocols wherever possible, and be able to ascertain if all our systems were shipping expected log volumes. Our previous platform did this well, via an agent that would remember logging state via checkpoints, and could load balance between multiple receiving servers. The security infrastructure teams, along with several other engineering teams at 2 Sigma, rely on this log data to troubleshoot outages and issues, so it's important it stays up and running. Our logs aren't always standardized to expected norms. Custom field additions and homegrown applications meant we needed to be able to have flexibility when it came to data parsing. We didn't want to have to shoehorn our own data into predefined fields or wrestle with logging logic that wasn't extensible to our environment. We use a common data model internally and wanted to adapt our new SIEM to that, not vice versa. Much of our log data is required to be retained for long periods of time, with some stored indefinitely. All of this storage can add up quickly if you're paying a third-party provider to host it and keep it accessible, but it's not free to do this on-prem either, both from a hardware perspective and from the operational overhead to scale out large clusters of servers. We also had to factor in sporadic operational costs for rehydrating log data that we had moved to long-term storage in order to keep our current system performant. And this ties into the next consideration, searchability. Given the quantities of data we were retaining, our old platform had a hard time searching large swaths of historical data. Searches that span months, i.e. looking through a year's worth of proxy logs to see if there were any web requests sent to an IOC, could take dozens of minutes to run. This delay could be further compounded if part of the search's date range had been sent to a frozen archive and needed to be activated again. We wanted to make searching as fast as possible to improve our incident responders' user experience. The other half of searchability that we were concerned with was how friendly the query language was. We were eager not to have to train our users on a proprietary syntax to use the platform. While we could have improved the performance of our on-prem solution by tossing more hardware at it, this was quickly becoming costly. Working in security and being at a security conference, this next requirement might seem obvious, but we needed to make sure the sensitive data we were logging was secure. We had to protect it not only from the outside world, but also the vendor hosting our platform, who could use administrative or root privileges to access it, and between teams inside 2 Sigma as well, who may not be authorized to access other teams' data. And lastly, since we rely on these logs for forensic evidence during investigations, we have to ensure our logs are resistant to tampering. Our last requirement was the need to generate alerts from our queries and scheduled searches. As I previously mentioned, speed is important here as well, especially in cases where we want to take automated actions. Our alert paths touch a variety of downstream sources, so the SIEM has to be extensible to support multiple platforms, including email, PagerDuty, Jira, and the like. One thing we didn't include in our requirement list was pre-canned queries. Our environment is fairly bespoke, and so most out-of-the-box queries from vendors require substantial tweaking to provide any value for us. Since we knew from the onset that we need to rewrite our alerts to work in whatever platform we were moving to, we didn't factor any pre-canned alert offerings into our decision process. Another omission was data parsers for a similar reason. Many of the data feeds our security team is interested in ingesting either had custom configured log formats or were from internally developed applications that didn't conform to a normal standard. As we'll explore further in the next section, this is one of the decision factors that may be starkly different for us than for other companies. The final consideration was our threat model. 2 Sigma doesn't run internet-facing web apps or the like, so our external and perimeter detection efforts are more narrowly focused. The majority of our threat modeling work goes into insider risk, which, given our largely customized environment, is unique to us. Most vendor software we looked at was highly targeted towards external threats and would have required substantial uplift to cover our threat model. So, with those requirements established, how did we wind up at our final decision to roll our own SIEM? The first factor we considered was cost to see if this was a non-starter. We broke it down into several sections, and the first is licensing. We'd already spent $1 million in the license for our third-party on-prem SIEM product, so moving away wasn't free if you don't believe in sunk cost fallacies, but we had a need to ingest more data than we were currently allotted. Getting to where we are now, plus some spare capacity, would have cost several $1 million more just for the initial license purchase. Additionally, we were paying approximately 18% in annual maintenance on the base license cost for software updates and support. The second cost component we considered was the infrastructure cost of running a SIEM on-prem, third-party or otherwise. It still requires the purchase of hardware, the operational overhead of lifecycle management, power, and data center costs. And these items tend to scale linearly over time if you have a long or indefinite retention period. By using a cloud service, we'd eliminate some of these, but we would still be paying someone else to store our data. The next item we factored into our calculation was business drivers. Many of the log generating sources we collected from were being moved from on-prem systems to GCP or other SaaS providers given the direction of the technology industry and choices being made throughout our company. The disconnect between generating this data in the cloud and bringing it in was increasing. One of our main log sources came from the business's usage of GCP, and its growth was about to outpace our 1 terabyte per day ingestion limit by itself. By putting our SIEM in the cloud, we'd be able to simplify and make log collection more cost-effective for these sources. This did come with the trade-off of having to ship our on-prem logs to the cloud, which isn't free, but wasn't as expensive, nor did it inject noticeable latency into our ingestion pipeline. Tying into my last point, since 2 Sigma's engineering and business teams were already making heavy investments into GCP as our cloud platform, we were able to hang on coattails. BigQuery offers 2 options to run searches: on-demand queries, which can be very expensive since you pay per byte queried, or through dedicated query slots, which are reserved at a fixed rate regardless of query size or duration. Our company had previously purchased a number of reserved BigQuery slots that are shared among our engineering teams, which essentially eliminated the cost to search our data within reason. We were also able to leverage negotiations other teams had done for data storage that drove our costs down. And lastly, the business had already established a dedicated interconnect between our on-premise infrastructure and GCP, which again reduced this project's overhead and improved our reliability and latency projections. I want to specifically call this out though. Our choice to roll our own SIEM was heavily impacted by decisions the business had made, and that may certainly not be the case for everyone. Our next consideration was the features offered natively in BQ and vendor products, and we drew up a comparison against our requirements. In recent years, the offerings in many cloud platforms have grown considerably to make building your own SIEM much more viable. Open source software has improved to better support mature methodologies for log collection. With either option, we'd still have to do work to normalize our logs, set up schemas, write down our own custom alerts, and other configuration steps. We dropped these considerations from both sides of the equation since they were roughly equal. This produced a result that we added to the cost component in terms of labor by taking into account what the overhead would be to reach our desired feature set if we built our own SIEM. At the end of the day, after we'd run out of envelopes to write on the back of, we made the choice to build our own SIEM with in GCP with BQ. I'll turn things over to Bret now for a deeper dive into our technical implementation.
Thanks, Ethan. So in starting this process, we centered our goals on reliability and simplicity, aiming to leverage native capabilities wherever possible. We set out to see just how much engineering work it would be to build the same must-haves we actually needed from our SIEM product, namely, first, batch file loads from system appliances. Most often, this takes the form of file dumps from security and network appliances, regularly FTP'd or rsync to storage servers, and loaded into the system of record. Second, streaming ingest from configurable sources. One use case is systems with a configurable remote syslog destination server or custom applications. Some examples include our mobile device management provider, some hardware appliances, and mail gateways. Third, scheduled query execution for complex logic, such as logic dependent on aggregation, multiple datasets, or patterns over time. For example, collect all similar events per hour, group by hosts, and inspect for a rate increase. And last, streaming alerting for single-line pattern matches. For example, single log lines that strike terror into the hearts of security personnel, like interactive login shell on SSHD logs on zero-touch machines, or tamper detection integrity alert. And, as bonus point items, we wanted to revision control and peer review our query logic and definitions in Git, and be able to flexibly ship output query results to various notification and tracking systems. Let's start with batch file loads. Many security and network appliances with high volume logs use periodically rotated local log files. In our environment, our network proxies, DNS infrastructure, and some of our firewalls are a few examples. BigQuery batch loads allow for ingestion of CSV or JSON files with associated schema definitions from local storage or Google Cloud Storage buckets. We chose to periodically sync our batch log files into a cloud storage bucket and then load them into BigQuery from there. This has the added advantage of allowing for simpler retry logic. It even permits us to fully drop all the historic data loaded to BigQuery and reload it with schema or parsing changes if we so choose. We use BigQuery itself to maintain simple metadata tables for per data source, per file ingest state, job failures, and parsing errors. That way, if some part of the data pipeline is interrupted or delayed, it can be picked back up, since the job will compare the set of existing files to the metadata table to see which need to be loaded. Admins can inspect the failed files in isolation, while the rest of the pipeline continues on working files. In our environment, some light tooling around the GCP, BigQuery, and Cloud Storage Python APIs does the following. Step 1. Given a configuration file of data sources, load files from inside our environment from an internal drop host to a specific destination paths in a Cloud Storage ingest bucket. Step 2. Create load jobs after querying a metadata table and comparing the results of what has been loaded to BQ to what currently exists in the bucket. In our example here, our job sees a file, file1.gz, for data source 1. If the file is new and has not yet been successfully loaded, we submit a BQ load job for file1.gz using the schema defined in our configuration for data source 1. And step 3. Store job result metadata by inserting it back to a different BQ metadata table. Failures are set aside so they can be retried. Next, let's talk about streaming ingest. Aside from the handful of batch appliances described earlier, the majority of our logs are pushed over the network either directly to GCP or to internal infrastructure for additional parsing, routing, and geographical load balancing. In securities logging infrastructure at 2 Sigma, we make use of open source tools for log forwarding. We rely on FluentBit for log forwarding, FluentD for intermediate aggregation, parsing, and routing, and direct calls to the GCP Cloud Logging API, formerly known as Stackdriver, for third-party integrations. I'll dive a little more into the specifics of each use case. For reliable log forwarding from our base Linux platform, we run a FluentBit agent and configuration from packages installed on the standard system image. In the majority of cases, we use FluentBit's direct GCP Cloud Logging output plugin to write directly to Google APIs, rather than ship to intermediate systems. This has a few advantages. 1. Having our large compute infrastructure route logs directly to Google saves us on maintaining a much larger distributed internal aggregator infrastructure. 2. Google's native capabilities in load balancing shifts operational burden away from us. 3. FluentBit is small, fast, and has low memory overhead, as well as having a well-supported output plugin to write directly to the GCP Cloud Logging API. For data sources requiring more complex parsing, routing, or enrichment, we use a set of FluentD aggregator instances that run in each data center. This is useful for bespoke systems with configurable syslog remote destinations and non-standard log formats. We also use this approach for appliances that may run in the DMZ that purposefully do not have direct connectivity to GCP, even via our direct interconnects. FluentD allows for flexible and performant parsing and routing for custom log formats. Lastly, we need to make fetching logs from an ever-growing number of hosted services simple and reliable. Our typical approach for vendor applications that do not natively provide logging integrations is to write periodic pull jobs and then push the results into the Cloud Logging API. We produce some internal tooling to make it easier for admins of SaaS services to write scripts to pull their API logs and then write them to our infrastructure. The goal was to make ingestion logic very easy for teams outside of security and shift the operational burden away from maintaining and developing all of these integrations to providing a standard, maintained set of tools for the teams to do so themselves. Altogether, these approaches have worked well for us. However, when we first deployed FluentBit to our compute environment, we did have a minor incident involving a need for additional cloud logging write quota when our changes hit the biggest deployment tranche. This was quickly remedied by GCP support after I submitted a carefully annotated rate graph to a support case. I warn you, I needed multiple levels of approval to exfiltrate this highly sensitive graphic. I think GCP support was so impressed with my MS Paint skill that they bumped our quota immediately. So, let's look at the lifetime of an event written to syslog on one of our base platform Linux hosts as a way to demonstrate how our streaming ingest works. First, an event starts its life being logged to the syslog socket on one of our compute hosts, sent from an appliance to one of a set of FluentD aggregators, or via a write to the GCP Cloud Logging Python APIs. Second, upon hitting the Cloud Logging API, BigQuery export filters are configured based on individual tags present in the event. Based on the tag, the event is routed to different BigQuery destination tables. In most cases, we use the log name value, which is uniquely configured on each data source, and specify the BigQuery dataset to write to. Last, Cloud Logging writes the event to the BigQuery table streaming buffer, assuming the event schema is compatible. The entire streaming process from on-prem log event to receive timestamp in BigQuery is usually less than 2 to 3 seconds. So that's how data streams in a few seconds to our BigQuery tables. Additionally, events in the streaming buffer are readable by queries to the table immediately. Speaking of queries, let's move on to how we designed a system based on native GCP components to execute and route pre-configured scheduled queries. After handling batch and streaming ingestion, we needed a consistent way to execute scheduled queries against our datasets. The resulting system looks like the following. First, we manage query definition files with associated metadata like MITRE attack tactics and techniques, output types and destinations, and query frequency in a GitLab repository. We use two-party merge request approvals for deployment or changes to query execution. In practice, deploying to production means syncing the configuration to a protected cloud storage bucket. Next, a set of cloud functions manages reading the query configuration files and executing the queries at designated intervals. Third, these functions output the results and metadata to pub subqueues, as well as writing them to BigQuery output tables for persistent result storage. And last, the result messages on those pub subtopics are consumed by another small tool that, based on the metadata initially configured in the YAML files, formats them into email, Slack, and PagerDuty notifications. This functionality, in addition to the data load and ingest capabilities, represents the bulk of the code we had to write to produce a SIEM in GCP. All told, across a handful of tools and infrastructure as code in Python, Go, and Terraform, we wrote somewhere around 6,000 lines of code. Next, let's talk about a simpler case, but a high-value one: near real-time streaming alerting. Monitoring a stream of incoming events for simple pattern matches enables quick detection and response workflows for many general cases. For example, let's explore detecting the use of a compromised SSH private key. Starting at the same point as our streaming and ingestion, an event is logged from SSHD on a machine in our on-prem infrastructure. The event is sent via FluentBit collection to the Cloud Logging API. Then we use a cloud logging filter expression to match specific events, in this example by inspecting the JSON payload.ident and JSON payload.message fields. Finally, upon matching the expression, the event is sent to a pub subtopic that is read, formatted, and sent to various output destinations. Now that we've covered ingestion and alerting, let's talk about how we manage access to our data. At 2 Sigma, our security-managed datasets vary widely in sensitivity and classification. Other teams outside security often leverage the bulk syslog collection for system-level troubleshooting or plant-wide upgrade efforts. When granting access to separate engineering teams, or even other users within the security umbrella, we needed the ability to granularly control access to our datasets. To accomplish this, we sync group ACLs from our internal directory service to Google Cloud Directory Service. These groups are populated into the BigQuery viewer role on each dataset, which allows us to separately provision access to more than 50 unique datasets. We use an internally developed multi-party sign-off system for adds to datasets to record approval. We also maintain audit logs of BigQuery query usage for forensic evidence of any internal misuse. Now, let's talk about some of our operational wins after completing this undertaking. We can elegantly classify our results into 2 sections, the no mores and the high fives. First, the no mores. Log rehydration. We never have to store, archive logs from BigQuery or pay any search speed penalties for older data. In our previous system, we often rolled off high-volume datasets in as little as 30 days because we didn't have storage capacity and index size affected performance. Too big for our SIEM is something we say far less often. In our previous system, we often deferred ingesting high-volume datasets due to size constraints. Now, the high fives. Query speed. We can run large queries over years of data interactively during exploratory or threat hunting work. And ingestion admin overhead. We onboard a few additional datasets every month and typically deliver with only a few hours of engineering work for each source. Next, let's take a quick look at some lessons we learned in the process. The first lessons we learned was that even during the lifetime of this project, much has changed in the GCP data ecosystem. Tools such as data flow and cloud monitoring may be more than adequate replacement for much of our own tooling and customization. Additionally, active monitoring in fast-moving environments can save you a lot of pain. We run daily integration tests against live GCP accounts to ensure we don't miss an API deprecation or response format change that can break our ingestion. This is specifically in the lessons learned section because we had to learn that the hard way first. And the note about costs. Much of our expense has been streaming very high volume logs. While the cost per byte is very low, for large datasets this adds up quickly. We're exploring converting some of those ingests to batch ingest to save money where we don't need low latency ingest. I'll now talk you through a recorded demo of a sample of our streaming detection patterns. Sorry folks, logging into the 2 Sigma network live at Black Hat was a tough sell to our compliance team. Okay, so we start with the shell on my Linux home server on the left, inside 2 Sigma owned and run data centers, and our browser on the right showing the GCP Cloud Logging Logs Explorer. I'll show you the filter expression we use to route the log entry towards our pub sub queue. Here, we're just inspecting for an accepted public key for root message from SSHD. Now I'll SSH to root on a machine with keyauth, simulating the use of a protected private key to SSH to root directly for break glass purposes. Looking at our logging filter again, we see the pub subtopic in the destination field. In a few moments, we'll see our Slack notification pop up in the bottom right-hand corner of the screen. When we click that, we're taken to a shared alerting channel that is one of our output destinations for notifications. That's it, and now back to Ethan for tactical results.
Thanks, Bret. Now looking at some of our tactical results. Let's start by summarizing the overall effort that went into building our own SIEM. As Bret said, we wrote around 6,000 lines of code for the necessary ingestion, routing, scheduling, and alerting functions. This coding work, plus the configuration of collection agents and aggregators, as well as the infrastructure in GCP, took about half an FTE year of effort to get an MVP, our minimum viable product. We spent an additional 3 months addressing some of the more complicated use cases we have to get to where we are today. These efforts have paid off, and we're now currently storing approximately 5 petabytes of data in BQ. All of our historical data is immediately searchable without any rehydration. We routinely ingest over 5 terabytes a day without concerns about overages or loss of function from punitive licensing terms. and our average query time is a matter of seconds, which is a vast improvement from the tens of minutes and upwards that we saw on our former platform. We estimate we've saved approximately $3.5 million in upfront license costs and an additional $600,000 annually in maintenance contracts. After the initial setup, our staffing resources required to support BQ are slightly less than what it took to support our former vendor's product and amount to about 1 person month per year. The largest reason for this is the reduced need to track down noisy loggers given the low cost of storage and negligible impact extra data has on search performance. So looking holistically, what did this effort do to advance our security program? For starters, we're much more agile when it comes to choosing datasets to collect. By opening up ingestion capabilities, we've been able to add more data feeds and free our security analysts to experiment on developing additional strategies that they weren't able to before. These include adding new external datasets to help match IOCs and the like, as well as adding larger internal feeds like firewall logs and certain network telemetry that enables more sophisticated analysis to detect anomalies and threats. For our end users of BQ, there was an onboarding cost to retrain our analysts and threat hunters to use standard SQL, but it's a more fungible skill set that has greater generalizability than a vendor's proprietary language. The analysts are also much happier because the time to complete a search is down, and that helps speed up investigations and incident response functions. The improved speed and reliability of our streaming alerting has allowed us to invest in near real-time detection and response for critical use cases. Given the security controls baked into the platform, we're able to open up select datasets and views to other engineering teams at 2 Sigma to help them troubleshoot and detect issues on their systems. This was also the case in our previous product, but we had to limit what we ingested from them given our sizing concerns, and often had to nag them when they were logging too much, which again is no longer the case. Our new platform also provides flexibility and extensibility in data integration and parsing controls. BQ supports complex record types, so doing things like blob JSON insertion works and is readily parsable. There are also no restrictions on ingestion methodologies, nor are we forced to use a specific framework for logging to match the platform's expectations. We're able to self-define our schema to match internal common data model with much less engineering effort, which helps to reduce cognitive burden on our investigators when trying to join datasets from disparate sources. So as we look toward the future of our homegrown SIEM, several areas for improvement and growth stand out. First, we are continuing to onboard and validate new datasets. Some are operational, like a new SaaS provider's logs. Some are tactical, like ingesting new threat feeds. Second, our choice for building our own SIEM in the public cloud has future implications, given how fast that area grows and iterates. We are considering making adjustments to some of the development work we've done to incorporate less labor-intensive third-party offerings into our SIEM workflow, such as Google's Dataflow. We also have plans to extend our response pipelines, first with additional automation to do things like isolate machines or disable access, and then later to also tie into legacy on-prem systems to handle additional response scenarios. Overall, the decision to roll our own SIEM has proven to be successful to date. It's enabled our broader event collection and analysis program to evolve and to continue to tackle the ever-changing threat landscape. With that, thank you everyone for attending, and we'd be happy to answer any questions.